Alright guys, hey, welcome back to another lesson video. Today we're going to talk about similarity transformations. In the previous lessons we talked about transformations, but they weren't similarity, right? In fact, make sure I clean the whiteboard here. So the previous transformations were called congruent transformations. I can't write today. I'm having a hard time writing. Isometry, another way of stating it. But reflections, translations, and rotations, I wasn't changing the shape. I was moving it, but I wasn't actually changing its dimensions. With similarity, we are, okay? And we talked about this a little bit throughout the previous lessons, but now we're going to devote like a lesson to this guy, okay? So first, a couple definitions. A dilation is a transformation that enlarges or reduces the original figure proportionally. That's a key part there. Proportionally, remember, that means that I multiplied every side by the same scale factor to get the new image, the new shape, okay? Center of dilation is a fixed point used in dilation. Don't you love definitions like that? Essentially, we're going to focus all of our dilations at the origin point, at the xy plane, okay? Which means that anytime we're finding a distance from the origin to the pre-image or image, that's going to be scaled proportionally to the scale factor, okay? And lastly, down here at the bottom, the letter K usually represents the scale factor of a dilation, okay? We know what scale factors are. We've been using them, but now we actually have a variable that we can attach to it, okay? Types of dilations. A lot of stuff on this screen. Let me just break it down real quick for you. An enlargement is when your scale factor is bigger than 1. So K value is bigger than 1. And a reduction is when your K value is between 0 and 1. We're talking about a fraction then. And we know that that does decrease the size of our image. Okay? So if this was my center point, let's say that was the origin, I can measure the distance from the center point to one of the vertices here of this shape. And then, if let's say my scale factor was a 3, I could take this distance and enlarge it by 3, by a scale factor of 3, to get my new vertex here, which would be T. Okay? Same thing here. And measure its distance from the center, and then triple that distance if the scale factor was 3 to get my new vertex there. Okay? Now, since all of our dilations are going to be centered around the origin, we won't have to worry about that. Okay? So what we're going to do, just real quick example, let's say I'm trying to go from A to B, and I want to determine if it's an enlargement or reduction, and then what would that scale factor be. If I'm going from A to B, I can see clearly I'm going from a large to a smaller shape. That's a reduction. And then what would the scale factor be? I'm glad you asked. Let's see. Pick any two sides. Now, I'm already telling you this is similar, so you don't have to worry about, do we have to figure that part out? We're going to assume it is. The side length here would be 1, 2, 3, 4. The side length on this guy would be what? 1, 2. I'm going from 4 to 2, so therefore I could say that my scale factor is a half, my K value. Okay? So once again, let me just write this down. It became a reduction, and my K value is a half. Now, a lot of people, which, tell you what, that was from what? 2 over 4, which was a half. Now, just from previous experiences, some people have a difficulty as to, what do we do? Does the 4 go first or the 2? How do I know? We'll go back to this guy, okay? If it's a reduction, you better make sure your K value is between 0 and 1. This better match. If I were to flip this and became a 2, that's not a reduction anymore, that's an enlargement, and that doesn't match this picture, okay? Does that make sense, seeing the differences? So just one example, just to do a quick reference for that guy, okay? All right, let's do another example. Photocopying. Let's say I want to photocopy a receipt that's 1.5 by 4 inches long, and I want to increase it 200% times the original image. What would be the dimensions of this enlarged image? Okay, so let me go ahead and bring back this whiteboard. So I'm starting The receipt is 1.5 by 4 inches. So this is what it looks like. And I'm going to enlarge it by 200%. And I want to know what would the new dimensions be when I enlarge it by photocopying this receipt. This right here is what 100% of the image looks like. If I were to copy it, no changes. If I'm going to double it to 200%, and notice I use the word double, then I can state that the dimensions would have to be double, right? I'm taking 100% and I'm making it another 100% larger than that. So 1.5 times 2 would give me 3 inches, and then 4 times 2 would give me 8 inches. So if I were to take this receipt and increase it by 200%, the new dimensions would be 3 by 8 inches. Okay, so that's what we would get for this guy. All right. Does that make sense? Now, let's go a little further with this example. Okay, let me go back to this guy. So this is what it looks like at 100%. Let's say I want to increase it by a factor of 430%. Okay, or actually, I'd say, well, yeah, let's say 430. Okay. What would the dimensions be? Well, you would take your 100%. To go from 100 to 430, I'm multiplying this guy by a factor of 4.3, right? Does that make sense? So I would multiply all these dimensions by 4.3, and that'll give me my new result, which, let's calculate it. Okay. So it'd be 6.45 inches, and then the other guy would be 17.2 inches. Okay. Now, we haven't done one in the reverse direction. Let's say I went in this direction. I want to make it smaller, so I'm going to decrease it by 50%. Now, if I'm decreasing it, that means I'm dividing everything by some number. So if this is 100%, 50% means I would divide it by 2. Okay, so I'd get what, 0.75 inches and 2 inches. That's what 50% of the image would look like. And I can continue, right? I can do 25%. If I'm doing 25%, I'd divide everything by 4, or a quarter of it, or I'd take half of the 50% to get to 25% of the image, and so forth. So just incorporating some percentages, we're still doing scale factor, okay? As long as you remember that this is what 100% looks like, to get to 200%, 300, 400, you would double, triple, quadruple it, and so forth. If I'm going the reverse direction, 50, 25, 12 and a half, and so forth, I would keep dividing by 2. Okay? Make sense? All right. A lot of different things in this lesson, huh? I'm trying not to go through every single example that I have in my notes. If I did, this would be easily an hour-long video, and that's not the point. The point is to go through a couple examples and explain the lesson content. My notes are online, so that way you can kind of see some of the other examples. Okay? All right, now moving on, okay, to verifying a simulation, to verify a similarity after dilation, okay? Now, what we're going to do is we're going to use triangles for a second. If I were to graph two triangles, and let's say I dilated one of them, but I want to make sure it's still similar, I could use side angle side and side 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 similarities to figure that out, okay? So for instance, here's the example that I want us to work with. I have an original image with these 3 coordinates, and I have this image with these 3 coordinates, okay? When you graph it, it looks like this, okay? Now, I want to verify that these 2 triangles are still similar. Let me write that up here. Similar? Question mark. I don't know yet, okay? The other thing I want to know is what's the K factor? What's the K value, I should say? Sorry. If it is similar. Okay. I can see that I have a pair of vertical and horizontal lines for both of them. And we know that perpendicular lines create right angles. We have an angle in common. Let me go ahead and find some side lengths. So OM, if I figure out the side length of this guy, let's see, it would be 3 and 6 more. See, the entire length of this guy would be 9. From M to N, let's see, from M to the y-axis, it's 6, and another 6. This entire thing would be a 12. Units, inches, whatever we want to measure. The length of this guy, if I start here at 1 and I go to 2, that's what, a total distance of 3. And then across here would be a distance of 4. It'd be 2 and 2 on the other side. Now, I don't know if you can see what I'm going for here. I'm verifying this by side angle side. The angle is right here in the middle, right? The sides, left and right of it, I'm trying to compare proportionally. 3 and 9, 4 and 12. Are they proportional to each other? Yeah, I think they are, huh? To go from here to here, I would divide by 3. To go from here to here, I would divide by 3. So, in other words, okay, looking at this, I'm looking at a reduction, and I know what you're probably going to ask. How do I know what direction I went in? Because O, M, and N, okay, are my original image, okay? My pre-image. The image was the smaller, okay, when I was done graphing it. That's how I know. This is a reduction. My K value is a third. And this would be similar by side angle side. Proof's done. Well, not proof, but problem's done. Okay? Wait, so far so good? Now, let's go a little further with this. Okay? And this is where we're going to get to the last part of the lesson. Notice, I didn't do triple S. And I could do triple S. I'd have to find the side length of these guys, which I can use Pythagorean theorem or distance formula to get to that point. Okay? And actually, I could use Pythagorean triples. Oh, there's a lot I could do with this now that I think about it. But, getting sidetracked. We're not going to think about that right now. I want you to look at the lines, individual lines for a second. And I want you to look at the coordinates too. So let's look at the coordinates first. I start with M, and then I go to D. My scale factor was a third, right? Remember how I divide everything by 3? If I divide this guy by 3, I get -2. Divide this by 3, I get -1. If I divide these two values by 3, I get the following result. And these two values by 3, I get the following result. That's interesting. So in other words, okay, let me write this down. The scale factor is being multiplied to the coordinates. Okay? So for example, what did I say? I'll move, don't worry. Sorry. Okay. So for example, okay, here's M and here's D. If I were to take each coordinate and multiply it by a third or divide by 3, I get these guys, which is my scale factor. That's brilliant, isn't it? So I can verify the points. The coordinates can also help me out, right, to see if it's going to be similar. Now let's think of slope for a second. What would the slope be? Well, let's take a look. This is a vertical line. This is a vertical line. Now, technically, vertical lines have undefined slope. Did that change when I did the scale factor thing to these guys? No, the slope kind of stayed the same, didn't it? Now look at the horizontal lines. Here and here. They're both horizontal. The horizontal lines have 0 slope. And did they change slope-wise? No, they didn't. But there is something that did change. Okay? So slope did not change for these lines here. But their location changed. Does that make sense? The location of this horizontal line changed when multiplied by the scale factor. Now, why am I making this point? Okay? It's a great question. You know, you ask a lot of really good questions. I don't need this no more. Goodbye. Okay. In fact, let me get rid of the PowerPoint off here So that way I can look at you guys and I can see if I'm in frame or not, which is really good. So why bring this up? Well, here's the deal. If I had a line like this, okay, and that's what? Y equals mx plus b. And I just made the statement to you that the slopes of these guys did not change when I multiplied by the scale factor, but their locations changed. Now, when looking at this line, m represents my slope. Now, that's not going to change, but my y-intercept will change, my b value. And why is it going to change? Well, take a look at this again. Okay? We established that the coordinates changed by the scale factor. We saw this visually and algebraically. Isn't my y-intercept a point? Let me give you an example. Let's say this is my line. Plus 5 is the y-intercept, but it is a coordinate point. It's 0, 5. Now, if I was to dilate this by a scale factor of, we'll use 5 again, by 2, this now becomes a 10. But, let me draw it up here, okay? So here is this guy at 0, 5. Up here would be 0, 10. But the slope stayed the same, right? It did not change, just the location of where that new line's drawn, okay? Does that make sense? So when it comes to dilating just lines, you don't change the slope, you're only changing the y-intercept by multiplying it by that scale factor. See how those connections are made there? Hopefully that became clear when I was explaining it, okay? What we're going to do is we're going to try one problem out when it comes to these lines, and that'll be it, okay? So let me go ahead. I'm just going to put the example right here. So here's an example. Okay. I have this line here. And let me just erase all this stuff. Sorry. There we go. All right, I have this line here. And I'm going to dilate this by a scale factor of 6. And I want to know what's the new equation of the line going to be. Now notice, this is not written in slope-intercept form. It's going to be hard to make any comparisons, and it's going to be hard to come up with the equation if this isn't written like this. Let's go ahead and do that first. I'm going to subtract 6x to both sides, okay, to isolate y. I get negative 3y equals negative 6x plus a 5. My last step, divide everything by negative 3. So I get a 2x minus 5/3. Okay? Now that's not the answer. That's just what the line is. We took it in this format and changed it a little bit. Okay? And let me zoom in a little bit. There we go. All right, now, what I'm going to do is I'm going to apply the scale factor, which is 6. Now, notice, going back to what I said previously, the slope never changed. It kind of remained the same. Okay? There we go. So the only thing that changed was the y-intercept. So what I'm going to do is I'm going to multiply the y-intercept by 6. Now, if you want to put this over 1, because you have a fraction next to a fraction, sometimes it's a little easier to see it. I'm going to write the answer over here because I'm running out of space. So my answer is going to be 5 times 6 is 30. 3 times 1 is 3. 30 divided by 3 is 10. So it's going to be 2x minus 10. So there's the equation of my line that's been dilated by a factor of 6. Okay? Now notice, same slopes, different y-intercepts. Sorry, same slopes, different y-intercepts, which indicates that we have parallel lines when we're dilating them. Okay? One final thing. Some of you might say, wait a minute, Mr. McCall, hold on. Okay, what about this? Okay, the slopes of these guys are the same. If you calculate the slope of this line and this line, you would see that they're going to be identical, okay? The only difference is where they cross the y-axis, okay? So I know I didn't mention those ones. I was just mentioning the horizontal and vertical lines, but this still matches what I stated previously, okay? And that's it. That's a lot in a, 20-some minute video. But we covered dilations, scale factors with a K now, reduction, enlargement. We did a photocopy example with percentages. We verified after we dilated. And here's the thing, guys. This is just a triangle. I mean, if I had like rectangles, which I do have in my notes, you would have to go back to all angles congruent, all sides proportional. Okay? I was allowed to use side angle side here because they're triangles. And then we wrapped it up with equations of lines when they have dilations involved. Okay? That's it. So I hope this helps. I hope you guys are doing well at home, and I will see you all in the next lesson video. Take care.